Today we are going to perform a circuit analysis of a parallel circuit. As you're listening to this, you may find it useful to refer to slide 18 in your electric current notes, which will remind you of the rules for voltage, current, and resistance in a parallel circuit. Just like with the series circuit, the first step is going to be to reduce your total resistance, or each of your individual resistances, to an equivalent resistance. One resistor that can replace all three of them but will behave in about the same way. The rule for resistances for parallel circuits can be a little bit tricky. 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and you could keep going on if you had more than 3 resistors. So this is probably the trickiest part and where most people could get tripped up. 1 over the equivalent resistance is going to equal 1 over 300 plus 1 over 200 plus 1 over 400. So if I add all of that together on my calculator, I'm going to get a decimal, or if you wrote it as a fraction, it would be 13 over 1,200. The decimal is 0.01083, and then 3 goes on forever, equals 1 over R equivalent. However, I want what R equivalent is. So I've got to basically take the reciprocal of both sides. Or on my calculator, I'm actually just going to type in, there's a button that says x to the negative first. That'll flip my fraction over. So when I do that, I get that the equivalent resistance is 92.3 ohms. So what I have just determined is that I could replace those 3 resistors with a single resistor of 92.3 ohms, in the circuit would behave in about the same way. I'm going to put that into my table too as the total resistance. I know it might sound a little weird to you to say that this is the total resistance because we didn't really add it up, but when I say total, that's what I'm referring to, the equivalent resistance. Now we're ready for step 2. Here it begins to look more like the series problem. We're going to use Ohm's law to calculate total current, so V equals IR. I know voltage in this problem is 9 volts. I know current. Well, I don't know current. I'm solving for current. And I know the equivalent resistance is 92.3. So when I solve that, 9 divided by 92.3, I got that the total current is 0.098 amps. So I'm going to put that in my table, 0.098 amps. Okay, so I've determined that my total current was 0.098 amps. Step 3, just like with the series circuits, is to carry back the constant variable. But I want to remind you that when we're talking about a parallel circuit, the constant variable is not current, it's voltage. So if I go back to my data table here, voltage is what's the same at all points in a parallel circuit. So at or across resistor 1, 9 volts. At resistor 2, 9 volts. Resistor 3, 9 volts. So the voltage in this case is the same everywhere. Now we're ready for... So now we're going to calculate the other variable. In this case, the other variable is actually current, because current is the one that adds. I'm going to use Ohm's law to do that. V equals IR. So if I want to calculate current is equal to voltage divided by resistance. So I'm going to go back to my data table and in each case take voltage divided by resistance. So if I look here, 9 volts divided by 300 gives me a current of 0.03 amps at that point in the circuit. 9 volts divided by 200 gives me a current of 0.045 amps. And 9 volts divided by 400 ohms, a current of 0.0225 amps. One other thing I'm just going to pause and point out to you is, as you would kind of expect, we have this phrase that says people and things tend to take the path of least resistance. Well, if you look, the current is greatest at the point in the circuit, the branch of the circuit that has the least resistance. And the path in the circuit that has the highest resistance is the lowest current. That means the fewest charges are going through there because it's harder to go that way. So that should kind of make sense. Finally, step 5. So step 5 is to make sure that the variable that should be added does add up to the correct number. In this case, the added variable for parallel circuits is I. So I total should equal I1 plus I2 plus I3. If I go back and check, 0.03 plus 0.045 plus 0.0225 should add up. When I added them up, I got 0.0975, which does correctly round to 0.098. So I have checked my work. It looks like I did the problem correctly.